Okay, we're going to talk in this chapter about vectors. Now, let me give some preliminary remarks here. We've seen vectors before. You think of vectors as either a column or a row of numbers. So you've seen a vertical stack of numbers or a row of numbers, that's a vector. Now, a vector is really a special case of a matrix. This is really a special case. If you have one row and n columns, or you can have m rows and one column. So you might wonder why we're talking about vectors separately. Well, we want to talk about the arithmetic of vectors. And once we've discovered and understood the arithmetic of vectors, we can talk about also the arithmetic of matrices. Okay, so let's go on and talk about this arithmetic. It's a generalization of ordinary arithmetic. Basically, when you do arithmetic with vectors, you do arithmetic on each number in the array separately. All right, so let's look at these arithmetic operations on vectors. All right, so we'll talk about column vectors first. All right, now again, he's talking about complex numbers here. We won't actually see any complex numbers for a while, but we are using that general terminology to allow for the possibility later. All right, so the vector space Cm, what does that mean? That means m copies of the complex numbers. It's the set of all column vectors of size m with entries from the set of complex numbers C. Okay. All right, now you could use the set of column vectors that have real entries. You can call that Rm. Both languages are very common. Okay. Right. So this paragraph talks about the conceptual understanding of vector. There are several different ways to understand vector. You can just think of it as a list. You can write it this way, or you can think of it as a point in higher dimensional space. Okay, or you can think of it as an arrow. Okay, all these different ways are useful ways of conceptualizing what a vector is. Now, you can certainly represent a vector any of these ways. Of course, if you have a 5-dimensional vector, it's kind of hard to draw it as a point in space, but you can still conceptualize it as a point in a higher dimensional space. Okay, so let's look at these operations on vectors. Okay. Column vectors are equal if every component is equal. So this square brackets ui means the ith component of u. Okay, so we have some examples here. All right, see, so for instance, if we call this vector b, if this vector was b, then you'd say b2 is equal to 24, and so on. Okay. Well, let's go back here. So two vectors are equal if every component is equal. So that's true. All right, now here he's making a point that's kind of important, is that you're now using the symbol equals in a different sense. When you say x equals 3, you're talking about x as being a real number. Here we're talking about equals in a different kind of mathematical object. Okay, so this is good to take this point to heart. Okay. Right, now we can write this system of equations as a vector equality. We're saying the vector on the right, consisting of these components, this, is equal to the vector on the left, consisting of these three components. Okay, so now we have a single equality instead of three equalities. Okay, it's called a vector equality. Now we can do addition on vectors. You do addition on vectors by adding each component separately. Okay. Again, now, okay, so he says this symbol plus is being recycled. We're using the same plus for vectors that we use for ordinary numbers. In computer, this is called overloading. If you do computer science, you may have seen something like this. So you're using the same symbol really for a different use, and you can tell what the plus means by the things that it's operating on. This plus here is operating on numbers. This plus here is operating on vectors. Okay, so here he does an example of summing two vectors. These are in C4 because there are 4 entries in each one. You add the vectors entry by entry and get the result. Okay. All right, now column vector scalar multiplication. To do scalar multiplication, you scalar multiply a vector by u by multiplying each component by that scalar multiple. Okay, so again, this is really a new type of multiplication. You're defining a times this u. So this au over here, that's actually a new definition. This a times each individual component, here we're using conventional multiplication. So this is conventional multiplication. This is a new multiplication. In some sense, you're sort of distributing the multiplication through all of the components of the vector. All right, notice that in the textbook, he will tend to use Greek letters as scalar numbers, scalar being not a vector, ordinary number, complex number, and these boldface as vectors. And that will depend on what book you are using. We'll use different notation. Okay, so here's an example of a vector in C5, and multiplying by the scalar 6 being an ordinary number, you multiply each separate component by 6 and get the result. All right, now here we're going to talk about some properties of vectors, and they're called vector space properties. Okay, later on we'll see what a vector space is. Suffice it to say, it's sort of a general characterization of any type of vectors. There are types of vectors that don't look like vectors at all. We'll see that later. We're basically here just characterizing general properties of vectors. Okay, so let's see what we have here. These are the important properties. The first one's called additive closure. If you take any two column vectors, then the sum is still a column vector. All right, think about that. That makes sense. Scalar closure. If you take any vector and multiply it by any scalar, you still get a vector. Commutativity. You can add two vectors in any order and you get the same result. Same as commutative for ordinary arithmetic. Additive associativity. If you add 3 vectors, you can reorder the parentheses. You can add them in any order. See, that's different from commutative. Here you're actually exchanging the order. Here you're just the which operation you do first differs. All right, we have a 0 vector. The vector that has all 0 components, when added to any other vector, will give you that same vector. We have an additive inverse vector. If you have any vector u, you can find a vector which you negate every component. If you add those two vectors, you get the 0 vector. Scalar multiplication associativity. I can multiply by one scalar, then by another scalar, and that's the same thing as multiplying the two scalars together before multiplying. Distributivity across vector addition. I can multiply the sum of two vectors by a scalar, and that's the same thing as the sum of the two scalar multiples. There's a lot of properties, but it's almost there. Okay, so another distributivity is I can add two scalars and multiply by a vector, and that's the same thing as multiplying the vector by the two scalars and then adding them. Okay, then we have a one column vectors that if I multiply any vector by the scalar 1, I get that same vector back again. Okay. So you could establish all of these, and basically you're always going to prove component by component. You go back to the definition. So follow this along here. He wants to show this distributive property. Okay. Now, if you apply this distributive property, the distributive property is this one here. What does this mean component by component? Well, if you apply this to one component, here we have, if you have the definition of, all right, so here you take a plus b times u and take the component of that. Okay. Now that's a scalar multiple times a vector. The definition of what it means to take the ith component of a scalar multiple of a vector is the scalar multiple of the ith component of the original vector. Okay. Now this u here is now a complex number. This ui is a complex number. So I can apply ordinary distributivity on this equation here. Okay. Now the definition of the ith component of of alpha u is just alpha times ui. Okay. The definition of the ith component of beta u is beta times the ith component of u. Okay. So you can read back and look at these definitions and see what he's applying here. All right, now the definition of the ith component of the sum of two vectors is the sum of the two ith components. Okay, so what have we shown? We've shown that for any I, the ith component of a plus b times the vector u is equal to the ith component of au plus bu. Now, since that's true for every component of the vector, that means that these two vectors, alpha plus beta times u, must be equal to alpha u plus beta u. Okay, and the others are quite similar. Okay. So let's look at this. Let's look at this comment here. Look at this vector minus u. This is a vector when we add to u, so the result is 0. We can compute minus u using other operations. So you can prove that the vector when added to u is 0 can be obtained by multiplying that vector u by minus 1. Okay, and here he's actually using scalar properties above. This property here is the definition of scalar multiplication. Well, suffice it to say that each step here requires a justification. We can leave that for the exercises. Okay. Now, this associative property, just like with real numbers, says that you don't need to be very careful about parentheses when you're adding vectors. You can parenthesize this way, or you can parenthesize a different way, because you can write the parentheses any way you want. Usually when you add vectors, you don't put any parentheses. Okay, that's it.